Okay, hi. Hi everyone, and welcome to this MAP webinar. The topic of the webinar, the title is Extreme Heat and Health, Creating Environmental Intelligence Through Science, Predictions, and Engagement. So this is a MAP webinar, but it's really more of kind of a demonstration of what the Climate Program Office is and what it does, the type of research that it funds. So this isn't just a MAP webinar. There are a number of programs in CPO that have contributed to the planning of this webinar. The RESA program, the Climate Variability and Predictability program, the Climate Ops Division all contributed to planning this webinar and also helped, get us in touch with some of these speakers that we're going to hear from today. So thanks to our partner programs here. The webinar is also going to speak to a new initiative led by CPO called the National Integrated Heat Health Information System. And Hunter Jones, who's a CPO colleague, is going to describe NIHIS. Did I do that right? Okay. Good. At the end of the webinar. So the idea behind this webinar is to demonstrate the unique end-to-end capability and focus of the Climate Program Office. Our various research programs support a broad array of work that's needed to develop new products, capabilities, and understanding of the climate system. This office supports getting buoys in the ocean, measuring and modeling atmospheric composition, understanding physical processes and climate models, modeling and predicting the climate system, assessing climate impacts and variabilities, and increasing community resilience through the use of climate knowledge and information. And we really do need this full portfolio and end-to-end portfolio of research activities in order to build informed capabilities and environmental intelligence, which is kind of a buzz phrase at NOAA lately, for the U.S. population. So the point of today's webinar is to demonstrate, through looking at the issue of impacts on health, how CPO builds robust capabilities by focusing on the full spectrum of research needs. We're going to start out the webinar with a talk from Andrew Marshall, who's at the Australian Bureau of Meteorology. BOM has developed a forecasting capability for extreme heat events that's geared towards increasing the preparedness of the Australian population for these events. And then the following four talks are going to focus on various funded research projects from the Climate Program Office and kind of cascade from fundamental physical understanding and observation and modeling of the climate system to prediction products, to understanding of heat wave variability, and then finally to providing information to communities. So the first talk in that series is going to be Qidong Zhang from the University of Miami. He's going to talk about observations and modeling of the Madden-Julian oscillation, which is a critical phenomenon operating at subseasonal timescales that has significant impacts on U.S. weather and climate at subseasonal timescales again. The second speaker will be Augustin Vencilios, who's at the University of Maryland, and he's going to talk about multimodal ensemble forecasting of extreme heat at subseasonal timescales. Brad Lyon's going to follow him up, and Brad's at the University of Maine, and he's going to discuss characteristics of U.S. heat waves. And then finally, Chip Conrad from the University of North Carolina is going to demonstrate a vulnerability tool that they have developed for extreme heat events. So the common thread with all of these talks is the subseasonal timescale. That's the timescale of interest here. And basically, it's going to demonstrate how knowledge and observations of the M.JO enable us to improve models, which can then produce better forecasts. And when you couple that with understanding of the phenology of extreme weather events, you can end up helping with the delivery of community-oriented tools for preparedness. And then we'll end the webinar with a little bit of an overview from Hunter on NIHIS. So, Andrew, are you on the line?
I am.
Okay, great. I'm going to transfer control to your computer.
Okay, let me know if you're getting this presentation.
Yeah, it looks good, Andrew. Whenever you're ready, go ahead.
Okay, well, thank you very much. Thanks for having me present to you this afternoon. I was about to say this morning, this afternoon. I do very much appreciate it, and I hope that this will be of some interest and use in your work there. So I'll be presenting on predictions of extreme heat that we've been focusing on at the Bureau of Meteorology on the subseasonal timescale over the last few years. The co-author to this work is Debbie Hudson. So Debbie also works for the Bureau, and Debbie and I have been leading the work on this topic. Co-authors are Oscar Alves, Lee Shi, and Griffith Young, also all from the Bureau. All right. So we know there's been increasing demand over the last few years, decade in particular, for subseasonal predictions. Now, there are many sectors that benefit, of course, from these forecasts, particularly health, of course, as we know, agriculture, energy, infrastructure, and so on and so forth. And these forecasts on this timescale really helpful for management decisions made on the kind of 2 to 6 week timescale. So this has been our focus. In 2009, we commenced a project improving subseasonal predictions, so just with regards to predicting climate anomalies, and that was a 3-year project. At the end of which we delivered some forecast products, and then following on from this, we commenced our project on subseasonal prediction of heat extremes. So just really extending the work that we've done into the extreme heat sphere. So there are, of course, as I mentioned, a lot of motivation from this work has come from the health sector. I've just put up a few newspaper articles from Australian newspapers here that came out around the summers over the last few years. So you can see heat-related deaths occurring, and also heat extremes affecting key sporting events. You're probably familiar with the Australian Open, and for those keen tennis fans amongst you, you probably know that almost every year for the Australian Open there are heat waves that occur. There was a particular tennis player a few years ago who hallucinated, collapsed on court, and that's not too uncommon. So of course, stretching right across the health spectrum, is really the broad interest in providing subseasonal predictions of extreme heat. Okay, so we started out. So the Bureau released a weather forecast heatwave service a few years ago. This was at the beginning of 2014, and it was for the numerical weather prediction timescale. And it was based on an excess heat factor index that was developed in-house at the Bureau by John Nairn and Robert Fawcett in 2013. And on the right there, I've just included the link to their technical report that you can read. And it outlines in detail their index. And this is based on human health motivations, really. So their excess heat factor index is comprised of 2 indices that they developed. One is the significance excess heat index, and the other is the acclimatization index. And I'll just briefly outline these. So the significance excess heat index is essentially where there are 3 days or more of high maximum and minimum temperatures that are unusual for a given location. So by unusual, we mean greater than the 95th percentile of climatology. And the equation is given there, so it's fairly simple. But then also there was an acclimatization component, and this is where the human health consideration particularly comes into play. So we know that typically heat waves at the beginning of summer have a more detrimental impact on human health than heat waves towards the end of summer because of the acclimatization that occurs during the summer period. So this has been taken into account as well. And so the acclimatization index is the degree of acclimatization which effectively compares the heat wave period to the last 30 days. And that's built into the equation as well. So that index value is higher at the beginning of the summer period typically compared with towards the end of the summer period. So when you take these components together, you produce the excess heat factor, and the map on the left is an example heatwave forecast for the beginning of 2014 using this index. And when the excess heat factor index value is greater than 0, this is defined to be a heatwave condition. And then we have essentially three degrees, I guess, of heat wave, or 3 categories of heat wave. and this is based on the strength of that index. So when the index is greater than the 85th percentile of all heat waves over the last 30 years, then that's a more extreme heat wave, which is called the severe category. And when the index is greater than 3 times the 85th percentile, then that's deemed to be an extreme heat wave. So we have these 3 categories. And we've adapted this NWP forecast to the subseasonal timescale, and I'll explain that in just a moment. Okay, very briefly outlining our subseasonal or seasonal prediction model, POAMA. So I won't go into too much detail here, but POAMA is currently run both in retrospective and real-time forecast mode at the Bureau. We are transitioning to the new Access model, which is based on POAMA and also based on the UK Met Office model system. And in both retrospective and real-time modes, we have 33 ensemble members. In retrospective mode, hindcasts are produced on the 1st, 11th, and the 21st of the month, and we have just over a 30-year data set. And in real-time mode, forecasts are produced twice per week and have been done since 2012. And we have an ocean atmosphere perturbation initialization scheme based on a coupled ensemble breeding. Okay, so applying to subseasonal heatwave forecasts, we really base our vision on this model from ERIE, where we have our Ready, Set, Go framework. So for monthly and seasonal forecasts, we can update contingency plans, allow volunteers to be trained, sensitize the community. On the multi-week timescale, the subseasonal timescale, which, as I mentioned, has been our main focus. This is where a lot of the capability has been missing in the past. So this timescale allows the assessment team to be mobilised, volunteers to be alerted, and communities to be warned, and preparation activities to be put into place. And then, of course, a few days out from a heat wave, we have the go aspect where we can activate volunteers and evacuate the community where necessary. So essentially, the way that we've adapted the NWP forecast to the subseasonal timescale is to produce probabilistic forecasts. So we calculate the probability, which is essentially the percentage of ensemble members of a heat wave occurring in either of those 3 categories at any time within certain periods. So the periods that we've defined are weeks 2 ahead, so a lead time of 2 weeks, 3 weeks ahead, fortnight 1 and 2 ahead. So that's weeks 1 and 2, week 2 and 3, and weeks 3 and 4, and also a month ahead. So we cover these various windows of time. And we've shown in a Bureau research report, which is currently in review, and if you'd like a copy of it, I'm very happy to send one to you if you'd like to email me. POAMA has generally good skill in detecting heat waves at all of these lead times, looking at the hindcast data set that we've produced. So these are some of the maps for the forecast product, and this is an example from January of 2013. So the observed map is on the left, and so this incorporates the 3 heat wave categories that I mentioned. And for this particular month, January 2013, Australia experienced quite a strong heat wave Australia-wide. So we can see that everywhere over the country there was at least a low intensity heat wave, and then the severity of that varied over certain regions, but most of the country experienced a severe heat wave during that month. And so this particular diagnostic for January shows the likelihood of a heat wave occurring at any point during that month. And so that's what the 3 maps on the right show. So the low intensity category, the severe, and the extreme. And these are probabilities, remember. So what we've done is to use coloured shading for probabilities greater than 50% and grey shading for probabilities less than 50%. And you can see that POAMA did a fairly good job of predicting the likelihood of a heat wave for this forecast initialised on the 27th of December. So all of Australia was forecast in the month to experience at some point a low intensity heat wave. Most of the country was also predicted to experience a high likelihood of a severe heat wave, and parts of the country an extreme heat wave. So particularly for forecasting the extreme category in this specific case, the model did quite a nice job, and this is one such example of providing information a few weeks ahead for those preparation activities to take place. These can all be seen on our experimental forecast product website, and that's just shown down the bottom there. So that's poama.bom.gov.au. You will need a password for that. So if you go to the website, if you're interested, you can simply request a password, and you'll be sent one, and then you can view these products. We've also produced some other heatwave products that are based on percentiles. So we've done a lot of our work has focused on the upper decile, but we've also produced products for the upper quintile and for tercile probabilities as well. So again, these are all probabilistic forecast products for the subseasonal timescale. So this is again looking at the same period. Now this is a week 2 and 3 forecast for the fortnight of the 3rd to the 16th of January 2013. So during that same heatwave period. Observations are shown on the left, and that's the maximum temperature anomaly. So you can see that much of the country experienced very high temperatures, greater than the climatology. And for each of those percentiles, you can see what the forecast was, again initialized on the 27th of December for weeks 2 and 3 ahead. So again, you can compare those maps with the observed and see that the model did quite a nice job for that event. So these are some of the examples of the products that we're producing. And the last example here is also based on decile 10. And on the left, I'm showing the number of hot days. And in the middle there, it's the chance of having more than the usual number of hot days. So again, it's based on the same percentile measure, but just different ways of conveying the information. On the right there, I'm just showing the maximum temperature distribution predicted compared to climatology. So the predicted is shown in yellow for different bins of maximum daily temperature, and the climatology is shown in grey. So you can see the shift in the distribution towards the right, towards the hotter end of the temperature curve there, which indicates warmer than normal temperatures towards that extreme end for this particular period. Okay, and just in closing, which I hope will segue into Jiong's talk. So we've also looked at relationships with climate drivers, and we found that there are windows of forecast opportunity. So various drivers provide subseasonal predictability for extreme heat at certain times of year and for certain lead times of interest and of use. So we've looked at all of these drivers, and one such example I'm showing is for the M.JO. We know that in our spring period, in your fall period, the M.JO in phase 3 teleconnects to a very high likelihood of extreme heat over the southeastern part of Australia, and that's what I'm showing there on the bottom left. And this is associated with a strong anticyclonic teleconnection to the tropics. And this work is outlined in detail in the paper reference I've given down the bottom there. So the climate dynamics paper down there. So we've looked at these climate drivers, and this has also gone into the work. We produced quite a few products on these drivers as well that you can view from the POIMA website. So to close with, in conclusion, we find that there's significant potential to augment traditional weather forecast warnings for heat waves to include guidance on longer timescales, and understanding the capability of the forecast system for predicting subseasonal extremes really underpins our potential future delivery of appropriate forecast products for these various sectors I mentioned, with health and agriculture being two of the key sectors that we deliver for. So thanks again very much for having me present, and I look forward to your feedback and any questions.
Yeah, thanks a lot, Andrew, and also, yeah, thanks for joining so early in the morning. It's like 6 a.m. there now, I think, 6:20, so really appreciate it. If anyone who is logged in virtually has a question, the way to ask that is to use the chat or the Q&A feature on WebEx. So you can chat a question to me or just tell me you have a question. I can unmute you, or you can pose it in the Q&A section, and then we can pose it to Andrew. While we wait for those to come in, are there any questions in the room here for Andrew?
Yeah, hi Andrew, this is Anarita. Very nice presentation. I had a question. You mentioned forecast of opportunity. Have you considered sort of integrating this information, you know, in some kind of hybrid sense into the forecast?
I'm sorry. Sorry, go on.
Have you considered using the information from potential conditions such as the M.JO phase or the IOD phase, integrating this information in together with a dynamical forecast into some kind of hybrid system? Are you doing something like that, or how are you using this information, for potential forecasts of opportunity?
Yeah, that's a very good question. Thanks for asking that. So at the moment, what we do really is to combine these various forecast products when we deliver information and advice. So if you go to the Polarma webpage, you'll see the forecast products for these different drivers as well as these extreme heat products. And on each of the driver pages down the bottom, you'll actually see the teleconnection maps like the one that I showed here. You'll see the teleconnection maps to extreme heat associated with each of these drivers. So the other thing that I haven't mentioned here, so I'm really glad that you've asked this question, is that just recently I've put together an integrated driver forecast. And so what that is in fact where for the 3 weeks ahead, I've produced a index plot effectively that shows all of these drivers and their forecast for the next 3 weeks. So you can see which of the drivers is active and which ones for which ones the phasing is neutral and so on. So when we look at a heat wave forecast, we can then go to this integrated driver map, and we can see what each of these drivers is doing. We can see what their current state is, what their forecast state is, and we can get a good idea for which of these drivers is influencing the forecast for heat wave. And we're just actually writing a paper now, Debbie and I, on that exact thing. So looking at these drivers, seeing what their teleconnections to extreme heat are, looking at their forecast for the next few weeks ahead, and matching that up with the forecast for extreme heat, and getting a good idea of which drivers are at play.
Thank you.
Julie, you have a question?
I do. So this is Julie Turton. I'm actually on the NIHIS side of things here, and I'm totally jealous because that's what we're trying to do, is sort of map all these things and how they're related on this end. So I might just steal from your stuff. It's a great concept. The other part of that question is, how is the information, so you've done this and it makes sense to us on the science side, are you working with folks on health or emergency management, and what are they asking for, and do they understand what this means, or do you develop something else? Is it just the red, yellow, green, and that's what they use? So how far down this path does your health community or your emergency response community go with you?
Yeah, so we've just started in the last couple of years to really interact with various departments. So, for example, a couple of weeks ago, there was a fire agency meeting in Melbourne, and we presented this work, and we presented in particular this framework that you should be able to see now, as well as these forecasts. And that process of going to these conferences and saying, hey, look, this is what we do at the moment, this is what we put together, how can this help you, and importantly, how can we tailor these products to your needs? And that's a big part of producing these products, is getting feedback from these various agencies and sectors. So we've done some work with the agricultural community. We've been to some of the meetings there, as I mentioned, with the fire agencies as well, all over Australia, and we're getting feedback on how we can tailor these products best to their needs. And the feedback that we've got so far is that we're hitting the mark pretty well at the moment with what we've produced. So we are very much looking for and encouraging this feedback process where we can hopefully improve these products and tailor them to the needs of various sectors.
Well, they're actually training on that Ready, Set, Go in Sri Lanka this week for the first time on heat. So you'll get some more feedback from that, and there's actually somebody from our Centers for Disease Control that's over there. I sure will have some information on that. So, yeah, thank you.
Terrific. Thank you.
Yeah.
All right, thanks a lot, Andrew. We got to move on to the next speaker, but appreciate your time. Thanks.
Thank you.
Okay, next up is Chidong. Chidong, are you there?
Yes.
Great. Okay, Chidong, I just passed control over to your computer, so if you can share your screen, that'd be great.
Did you see my screen?
Yeah, we can see it.
Okay.
Let's go. Whenever you're ready, go ahead.
Okay. So thank you, everybody, for listening. And I'm going to give you a very brief summary of the main results coming out of the Dynamo Field campaign that are directly relevant to M.JO prediction. As we know, M.JO provides the main source of predictability on the subseasonal timescale. And the Dynamo Field campaign took place in 2011-2012 with the main objective to improve our understanding of the key process for M.JO initiation and to improve our capability of M.JO prediction. And since the completion of the field campaign, and there have been about 120 publications, and there's absolutely impossible for me to summarize all of them. So I have to be selective, and by selective, I'll have to be subjective. So this is what I decided to talk about. I'll first briefly talk about the new M.JO prediction skill measurement, and then I'll go through some nitty-gritty process over the Indian Ocean that we found could be crucial to the skill of M.JO prediction. And one is the shallow convection, and the other is upper ocean warm layer and ocean memory of M.JO. And finally, I'll talk about a radar retrieval of microphysics, and that's something very, very new. So my presentation will not touch upon directly the feed waves, but mainly talk about how we can improve our M.JO prediction model in terms of accurate processes that may lead to better heat wave prediction. So let me start the M.JO prediction skill. And there's a quite number of publications since Dynamo focus on prediction skill of M.JO initiation over the Indian Ocean. And as we expect, the moisture field is one important part, and air interaction is another one, even though it's a case dependent, and dyno cycle is another one. And the three of them actually related. As I will go through my presentation, you will see. And the fourth one is when we compare two different M.JO prediction model scales, we found that the synoptic scale variability is very important. A lot I'll talk about the measurement. Okay, maybe first I'll talk about the measurement. So what you see here is the error growth of prediction scale during Dynamo Field campaign. The red curve represents the NSAT GFS, and the black curves are for European Center IFS. Generally speaking, the error growth is faster for NSAT GFS than the European Center. You don't have to worry about the dashed line and solid line. It's just a cross-validation. Dash is to validate by their own reanalysis, and dash line is validate with the other reanalysis from the other model. So, so if you see this, you find out that the NSAT model error growth is faster than European Center. And on this upper right corner is the larger scale error growth rate. Larger scale, by definition, is the zonal scale larger than 20-degree longitude. And you can see the GFS growth is larger than European Center. But the most striking, and that's what we did not expect, if you look at a synoptic scale error growth, it's much faster than the larger scale. And that we think this synoptic error growth actually really is the reason that that difference between the NSAT forecast scale and the European Center forecast scale.
Hey, Qidong, I'm sorry to interrupt, but we're wondering here what variables and fields we're looking at here.
This is the using the zonal wind. Each is variable. Yeah. And
what level are we looking at?
I think this is 850 millibar.
Okay, great. Thank you.
Yeah. And on the bottom right is the mesoscale. You can see mesoscale by definition is the the scale is less than 5 degree, zonal scale less than 5 degree longitude, and it does not make any difference. So it's the larger scale and the synoptic scale, but the fast growth is not synoptic scale. So that's something new we didn't anticipate. And then in terms of measuring the M.JO scale, the most common matrix is the RMM index, and most of us are familiar with it. So on the top shows the RMM index measured correlation between European Center forecast and the reanalysis for November 2011 M.JO event. And you can see that the correlations remain pretty high until up to day 15, and this is the root mean square error growth. But if you look at this, and you can see up to 15 days, the European Center model maintained pretty good forecast scale based on this measurement. However, if you look at another different measurement that focuses on precipitation, we know the RMM index is weighted more by the upper levels of the wind. If you look at the precipitation per se, there's several new methods tracking the M.JO precipitation eastward movement, and if you use that as a measure, you'll find that by 15 days, look at this panel, the amplitude of precipitation has dropped more than 60%. So even though the correlation is still high, the amplitude is very, very different from the reality. And the initiation date is off by 5 days. So I guess the lesson learned here is we treat the RMM index as a measure of a global scale, and we can treat this precipitation tracking measurement as a local scale because it really follows the M.JO Convection Center moving eastward from Indian Ocean to the Pacific. And that is very important because if we want our model to predict not just the M.JO index, but the M.JO teleconnection. The teleconnection is forced by the location of the connective center. It's not by upper level zonal wind. So this local measurement is crucial to get M.JO convection prediction scale assessment right. Okay, let me quickly move to another topic, that's the shallow convection. And based on dynamic field observations, we found that during the suppressed phase and the transition from suppressed phase to M.JO initiation active phase, there's a period of time that you can find the local FST have a diurnal cycle showing at this third panel from the top. So this is the different measure of FST and surface latent heat flux. You can see this diurnal cycle. And what happens is this FST diurnal cycle can force a diurnal variation of shallow cloud. And you have a diurnal initiation of shallow cloud in the noontime and then precipitate a little bit in the afternoon and dissipate in the evening. And associated with this diurnal variability of shallow cloud, you have a diurnal variability of moisture. So this measured by this blue color. You can see the gradual increase with the diurnal variability and then gradually increase on the M.JO time scale that shows on the top panel. You can see the blue color gradually become higher, deeper. That tells you the moist layer become deeper, deeper. Eventually, it will reach the point that M.JO initiation starts. So this is very interesting. It tells you that the shallow convection react to FST diurnal cycle and give you the moistening on the diurnal time scale that gradually rectify into M.JO scale. Now, this FST diurnal cycle actually happened within a very shallow layer in the upper ocean. So this upper panel shows the sea glider measurement of a time series of temperature as a function of depth in Y and the time. And you can see this red color represents the diurnal cycle of the upper ocean, and the surface diurnal cycle is what we saw from FST. And during this period of time and leading to the M.JO initiation and the diurnal cycle, if you make a composite, you can see it's very shallow. The main part of it is only in the top of 5 meters. And this is what we call the warm layer of the upper ocean. And most of the current global ocean prediction model does not have the resolution to resolve this. So it won't be surprised that they will not capture this dino variability in the upper ocean. And that will probably trigger to the atmosphere that we're missing the dino cycle in shallow convection and it's moistening in the lower troposphere. Continue the theme of shallow convection. One thing we find that's surprising is the cold pool that produced by shallow convection. Before dynamo, we all knew that the deep convection can generate strong cold pool, but during dynamo period, the radar, especially the NCAR S4 radar, is so sensitive that actually can see the cold pool generated by shallow convection. So all those radar images were produced during the suppressed phase of the M.JO. Then you can see this ring, the green ring, and this tells you the edge of the cold pool here, and the one here, and the one here. And the pink and the yellow color represent convective radar echo. So convection form the outside of the cold pool, even those cold pools are pretty weak because they're produced by shallow convection. But those convection actually can grow into a deeper one, especially when you have two cold pool intersect with each other. And at intersection, the convection can go really deep. And this is something surprising. And actually, this happening very common during the suppressed phase and during the transition phase to M.JO initiation. And we think this represents a very important role of shallow convection that leads to the development of deep convection. But shallow convection is very difficult to observe because from satellite, you often have this high cloud to blocking the view, and the cloud radar that can see a shallow cloud suffers from attenuation by precipitation. But we found a way to solve the problem through dynamo observations. At the Adu Atoll, we deployed two radars. One is S4 radar, which is the precipitation radar, and the other is the KZAR, which is the cloud radar. And S4 radar can see heavy precipitation but does not see shallow non-precipitating cloud. This KZAR radar can see shallow non-precipitating cloud but suffer from attenuation by precipitation. But you combine these two, you can derive an algorithm that allow you to screen the attenuate radar echo. So you can use a cloud radar alone to isolate the shallow cloud. And we did that and then apply to more than 10 years of observation at Manus, which was the DOE ARM site, and they have a cloud radar deployed there for more than 10 years. So we have a lot of cloud radar data. Before Dynamo, we cannot use this effectively because the rainfall attenuation. With Dynamo data, we developed the algorithm. We can screen out the attenuation and get more accurate detection of shallow cloud. And turns out that we use these 10 years data to composite the shallow cloud and its moistening to lower troposphere through the life cycle of M.JO over the Western Pacific. And what we found is both non-precipitating and the precipitating shallow cloud have play a very important role in moistening the lower troposphere continuously through the entire M.JO cycle. And this is a very important part of the water budget, moisture budget of the atmosphere in the lower troposphere. Okay, now the last slide I want to show about the shallow convection is in the modeling. And we all know that the deep convective cumulus polymerization is very important in M.JO simulation and forecast. And we did some simulation that demonstrate that the shallow convection is also important. So this is the one event, is the Dynamo November case. You can see the two bands of carbon wave together, they define the one M.JO event to the left. And the second panel is when we use a global model with a 15-kilometer resolution with both deep and shallow cumulus polarization, we can produce these two rain bands. And you notice that we call the maritime continent barrier effect because the M.JO in this simulation does not propagate through the maritime condiment. But what interesting is if you turn off the shallow cumulus polymerization, only let the deep convection to work, the simulation become, the M.JO, simulate the M.JO become much weaker. You miss the second case. Then if you use shallow convection polymerization only, you have two ring bands that become much less organized. So the lesson learned here is you need both shallow and deep convection. And up to this point, we pay a lot of attention to deep convection polymerization, and we should pay equal attention to shallow cumulus polymerization. Okay, let's move on to the ocean memory. What we found what interesting is when we have a very strong surface wind associated with M.JO, the first ocean, that generate a very strong ocean surface current. And that current represented here in the second panel lasts longer than the surface wind itself. What interesting is after the M.JO is passing over, and the M.JO is over, there's no surface wind forcing anymore, you still have this very strong vertical wind shear, current shear at the bottom of the mix layer. And that translates to shear generates the mixing at the bottom panel here. You see the very strong mixing, the red color. And this mixing actually continues for 1 or 2 weeks after M.JO passing by. And that serves as a memory of the M.JO in the ocean. And that actually provide a continuing exchanging between the upper part of the ocean and the deeper part of the ocean. And that is very important to upper ocean heat budget. The last part I want to show is the microphysical retrieval from a radar. We have this dual polarimetric radar capability that allow us to identify different hydrometer types, such as grapple, light rain, heavy rain, in different parts of the convective system. So this cartoon at the right-hand side gives you an idea of what can be composite based on radar observation. So this is a convective signal. The arrows represent the updraft, and different colors represent different type of hydrometers. And you can do this for stratiform precipitation too. And the value of this is the first time and we can actually retrieve three-dimensional distribution of hydrometer within cloud system, and we can use this to validate our model to a higher degree. And if we wish to develop global cloud permitting model for subseasonal prediction, and we definitely need this information to validate and to help development of those kind of models. So my take-home message is, number one, there's several processes that are very important to M.JO prediction, and we have not paid enough attention up to this point. One is the shallow convection and its diurnal cycle, and synoptic variability, the warm layer of the upper ocean, and the turbulent wind-driven shear-generated turbulence mixing in the ocean. And these all require higher resolution in the model that probably has to be much higher beyond the current configuration of operation models. The second one is we have the wonderful new tool to retrieve microphysics that give us some information for us to develop cloud permitting M.JO prediction models. The last one is we need both global and the local measure of M.JO prediction scale. That's it. Thank you.
Okay, thanks, Qidong. That was great. I think in the interest of time, we have to move on to the next speaker, but thank you for calling in. That was an interesting overview of some of the Dynamo results. Okay, so next speaker is Augustin. Augustin, are you on the line?
Yes, I'm here.
Okay, great. I'm transferring control over your computer. So just, yeah, great. No instructions necessary.
So, Dana, are you the right?
No, we're not seeing that. We're seeing your notes view. So if you can just flip it back, that would be great. Perfect.
So today I will be discussing the importance of multimodal ensemble techniques in forecasting excessive heat events at subseasonal lead times. I have to acknowledge my co-authors and NOAA for funding this work, and also thank CBO for this invitation. So I will first define what excessive heat events are, and then based on this definition, I will develop a monitoring system, a baseline forecasting system, which I will try to verify the skill, and then finish with discussing the multimodal ensemble techniques in this kind of forecasting. Now, we all know that heat kills, and a good example for that is the July 1995 heat event, in which more than 700 actually people died from heat in the larger Chicago area. What happened then is during the week from basically July 11th to July 17th, there was a very flow of very warm air crossing the Corn Belt and pumping tremendous amounts of humidity, and this resulted to dew points that were in the low 80s over Chicago, and a heat index up to 125 degrees. So one of the problems in defined excessive heat events is that in comparison with other natural hazards, heat is a silent or invisible killer. We can see sometimes effects from heat, like for example in this case is the heat wave that struck India back in May 2015, and you can see the asphalt melting. But we have to define, but it's basically it's a silent and invisible killer. So we have to be very careful about how to define this heat event before monitoring and forecasting them. So in defining excessive heat events, we consider the ingredients of the heat events, and we know that the impacts of heat events grow non-linearly as the temperature and humidity increases, and this lead us to the requirement to use for using apparent temperatures that are based on models of the physiological effects of heat on the human body. In this work, we use the NOAA's heat index. Also, we know that the impacts of heat events increase as a function of their duration. And this, for example, a heat event of that lasts few hours has different amount of, will have to be prepared differently than for a heat wave that lasts 2 days, 3 days, and so on. So we have this requirement for our definition to use to take care of this need for consecutive days with high apparent temperature. Also, we know that the impacts of heat events depend on the geographical location. 100 degrees Fahrenheit in Seattle is not the same as 100 degrees Fahrenheit in Atlanta. And finally, high apparent temperatures are felt differently as a function of time because of the acclimatization, and therefore we have to define what is high apparent temperature as a function of time within the warm season. Now, based on these considerations, we define heat events using percentiles of apparent temperature. We first define a heat day as a day with maximum heat index exceeding a given percentile alpha for the geographical location and time frame within the warm season. A heat event now can be defined as a succession of at least 2 heat days. And we can define heat events at different levels of intensity. For example, when the alpha threshold is 90%, 95%, and 98%, we have events at level 1, 2, and 3. The benefits from this definition is that we are addressing both the physiological effects of heat and challenges of subseasonal ensemble forecasting. And of course, it's easily expandable to week 3 and 4 and to seasonal forecasting. Now, the inconvenience is that we need expensive reforecast and lengthy historical records of temperature and humidity. Now, once we have defined what heat events are, we can start doing interesting things, like, for example, developing and monitoring excessive heat events for weekly periods. And we do that by defining a heat week as a week that contains at least 1 heat event. And then we can also define a start date of this heat event within the week and the duration of this heat event within this week. For example, an example is of this monitoring system is the description of the July 1995 heat event that I'm showing in in these panels on the right hand, on your right side. And the first panel shows the occurrence of the heat event at the three different levels of intensity. And we can see that a level 3 heat event, in which the threshold for the threshold is at 98%, was covering an extended area from the upper Midwest to the Northeast and Mid-Atlantic. The second panel, the central panel, shows the start day of the event, and we can see that in the middle of the country, the event started about the beginning of this period between 11 and 17 of July, and ended, and in the Northeast and the Mid-Atlantic, it was occurring at towards the end of this period. This shows us that this event had eastward propagation from the middle of the country towards the Northeast and the Mid-Atlantic. And finally, the third panel shows the bottom panel shows the duration of the event at intensity level 1, and we can see that around the area of Chicago, the event lasted more than 5 days, explaining how the increased numbers of casualties then. Now, again, once we have this definition of what a heat event is, we can start doing also chasing sources of subseasonal predictability for these heat events. And here I'm showing a composite based on 42 cases from 1948 to 2015 that resemble the Chicago 1905 event. The left-hand side panel shows this the structure of these events, and compositing weekly mean geopotential anomalies at 500 hectopascal. For the upper panel shows the week during the week of the heat event. The central panel shows what was happening 1 week before the heat event, and the bottom panel shows what was happening 2 weeks before the event. And you can see that a very interesting high wave number structure occurring in even from a week -1, and probably having some seeds in week -2. And these are patterns that are similar to the ones that were recently reported in the literature. And finally, having defined what heat events are, we can start doing forecasting. And here is our baseline system. We use the NCEP GFS, the 84 ensemble members per day. And what we do is for each ensemble member, we compute whether week 2 is a heat week, the starting day, and the duration. Having this information, we can now compute the statistics, the probability of occurrence, the mean start date, a day, and the mean duration. The central panels show, for example, a forecast that was initialized on June 18th, 2015, and targeting the week between the 26th of June and the 2nd of July, 2015. And you can see the probability of occurrence of heat events for different levels of intensity. The upper one is intensity 1, level 1, level 2, level 3. And we can compare that to also with what the climatological heat day for the given week is. You can see these on for the appropriate level of intensity, and you can see these panels on the right side. And the red line indicates the ISO line of 100 degrees Fahrenheit heat index. Now, what happened? The verification. What happened during this week? It can be seen in the lower left panel. You can see that there was a heat event in the Northwest during this period, and basically it was the first heat event of last year's warm season. Now, we of course have to verify such baseline forecasting system, and for this we are using the reforecast of the GEFS from 85 to 2014, and we are based on receiver operating characteristics, the ROCs, and the corresponding area under the curve, AUC. So basically what we are doing here is to create a contingency table for each of the grid points over the U.S. and compare observed events versus forecast events. And we can define a forecast event when the probability of occurrence of its event exceeds a certain number P. Now, the ROCs are the relation between the probability of detection versus the probability of false detection for different values of this threshold P. And for example, on the right-hand side, the upper panel shows one of these ROCs for all the grid points over the United States. Now, what's interesting here is that the area under this rock curve can give us a measure of the forecast yield of the system. In fact, if this curve was on the blue line, over the blue line, that would mean that the probability of false detection of an event is equal to the probability of detection, meaning that the system is worthless. But values above this 0.5 show us a system that has some forecast yield. And of course, the higher the values, the better the system. So in the lower panel, I'm showing the AUC for L1 events, the GEFS. And you can see many areas of light blue colors. This means that the AUC exceeds 0.65. And then quite a few grid points with values exceeding 0.7, reaching 0.75, and even going up to 0.8. So this means that our baseline system has some forecast yield for week 2, for heat events at week 2. Now that we have this baseline system, we have to find ways for improving it. And of course, the first way to do that is to investigate physical reasons for successes and drawbacks in forecasting the specific heat events. Meanwhile, though, we have to continue doing the forecast, operational forecast, and that's why we have to use statistical processing, post-processing, to bias correct and calibrate a probabilistic forecast. For example, these panels show a reliability mapping of the probability of occurrence of the Chicago event, forecasted 2 weeks in advance for the GFS, and we see that this reliability mapping decreases the probability of occurrence, meaning that as most of the models, this model is overconfident when forecasting heat events. Now, the third way to improve our baseline system is to use multi-model ensemble forecasting approaches, and here is why. Here I'm showing the AUC for 3 different models. The ECMWF is the upper row, the GFS and the CFS, and the results from combining these models. So the upper row shows week 1, week 2, week 3 ECMWF AUC, and you can see, of course, how quickly the forecast skill drops from week 1 to week 2 to week 3. Now, what's interesting to notice is that when combined the week 2 GFS to the week 2 ECMWF, we obtain the results shown in the bottom row, and which clearly are better than the best model, which is the ECMWF. So it's important to do these combinations at week 2. And at week 3, you can see that when combining the ECMWF model to the CFS week 3 model, we get AUCs that, especially in the Northeast Corridor and the Mid-Atlantic, are much better than the pure ECMWF model. So in summary, we quantified heat waves using a definition that takes into account both human physiology and the constraints of probabilistic forecasting. And based on this definition, we developed monitoring systems and a baseline forecasting system using the NCEP GFS. Now, this system is capable of detecting heat events 2 weeks in advance, of course, depending on some areas are better than other areas. And we also investigated multimodal approaches, combining GFS and ECMWF for week 2 and CFS and ECMWF for week 3, finding that these combinations, these multimodal approaches improve our forecast skill. Our current and future work is that by next week, we are going to start producing daily experimental forecasts for week 2 heat events with the GFS and providing them to the Climate Prediction Center forecasters for evaluation and eventually for their feedback and improving the system. And down the road, we will augment this forecast capacity by including predictions based on the ECMWF week 2 forecast and use models as the CFS from the NMME from the NMME models to extend the system to week 3 and 4 and to the global subtropics and tropics. And that's all I have.
Great. Thanks a lot, Augustin. I think we have time for one quick question. If anyone would like to ask, you can type it online or here in the room. Any questions for Augustin?
Yes. This is Julie Turton, Augustin. Thank you very much. The experimental forecast you're about to launch, are we doing anything to get them out? I know there's some folks from CDC on the phone, they're partners in NIHIS. Are we testing or validating with them, like getting it out to health people directly, or is it just posting it online? Or I realize it's experimental, but could we do something to engage the public health side now in that testing phase?
At this point, what we think of doing is that the forecasters will be using this information and provide forecast like the one that I'm showing. That's a mock-up forecast, like the one that I'm showing on the screen right now, where areas of high risk, moderate risk, and slight risk for a heat event will be drawn. And also, they will be providing a starting date and duration of this event.
Okay, thank you.
Great, okay. Oh, you know, there's actually a question, Augustine, that just popped up in the chat, so I'll just read this out. It's from Kim Knowlton, and she asked, have you surveyed the range of different optimal lead times for forecasts among different users, that is the health user community, agricultural users, infrastructure planners, et cetera?
I have not, and this would be a very interesting collaboration if someone would like to work with us.
Okay.
We can help with that.
Yeah, Kim, if you're on the line, you can hear, I can connect you guys after the webinar is over. Okay, thanks a lot, Augustine.
Thanks, Tom.
Next up is Brad. Brad, you on the line?
Yes, can you hear me okay?
Yeah, sounds good. I'm transferring control over to your computer right now. And just share your screen with us, please.
Does that work?
Great. Yeah, it looks great. Whenever you're ready, Brad, go ahead.
Okay, thank you very much. I'll try to keep this brief. This is going to be a sort of a subset of activities that's involved in a project that I'm working on that's funded by NOAA, Climate Observations and Monitoring, a project that I started actually at the IRI at Columbia University, where I spent the last 16 years before heading up to the University of Maine. So this is work I'm collaborating still with Tony Barnson on at the IRI and Columbia University. And basically, the idea is that as we all recognize, there's no universal definition of a heat wave. You know, we're immediately faced with the idea of which variable do we want to consider. It seems obvious at first, perhaps, well, temperature, right, but do we mean, you know, daily maximum, minimum, mean temperature, both maximum and minimum? How do we include humidity if we want to? One methodology I'm going to use is the so-called apparent temperature, which I'm going to be calling T sub A here, but that's really just a heat index that others have alluded to, how humans sense the temperature is in terms of their cooling requirements and ability to cool. So that's an example I've shown here under heat indices more generally, and there's actually several of them. A more physically based way to incorporate humidity is something called the equivalent temperature. And all we're trying to get at in showing these different variables is that we expect different types of behavior depending on how we look at this. Similarly, with the magnitude or the threshold that we use for defining a heat wave, do we want to use an absolute scale or relative scale? In our work, we're choosing a relative scale due to regional differences. We're looking across the United States. And again, durations. Do we want to look at, you know, extreme 1-day heat, 3 days, 5 days, and so forth? So what this project is trying to get at is, from a physics perspective or a diagnostic analysis, we expect differences in behavior of heat waves based on their definition. For example, what's the frequency of occurrence over the last 50 years of heat waves depending on definition? How do those persistence characteristics differ depending on the definition of the heat wave? What's the spatial distribution of these various types of heat waves? And the reason we're interested in that from a practical point of view is that we know from an impacts perspective that we expect differences and I'm calling it sensitivity to the heat wave depending on the definition. So for example, today we're talking more about health, but could be the energy sector, agriculture, and so forth. So I'll try to just show a few slides here to try to get at the main ideas of what we're trying to get at. So what I'm plotting here is using the North American regional reanalysis. We're also using station data quite a bit in this study, and ultimately we're going to compare this to the behavior in the CMIP5 simulations before looking at how they behave in projections. But what I'm trying to get at here is how these different temperature variables, and including moisture, behave differently. So these are just measures of the standard deviation within the North American regional reanalysis over the summer months, June to August, 1979 to 2014. So up in the upper left here, we're looking at maximum temperature in the NAR. And we see, you know, there's a broad pattern of the standard deviation increases as we head to the north. The variance tends to be lower where it's the hottest, and that makes sense in the summer that the storm tracks has moved northward, and so, you know, the mixing of the cold air with the warm air is occurring in the northern part of the country. And of course, there's a lot of regional variations related to things such as coastlines. Here you see up in Hudson Bay, depending on the wind trajectory in that region can affect the variance of the temperature, and of course, things like mountains in the western U.S. So that's temperature. If we want to include humidity, here's one measure of humidity that I'm using, the specific humidity, Q, just the grams of water vapor per kilogram of air. And the variance pattern there looks quite a bit different. I'm not showing it here, but actually in the summer months, the highest specific humidity, the most moisture in the air is here in the southeastern United States. But the greatest variance is to the north of that. Occasionally that warm and moist air will move northward, but at the same time, other times you can bring cooler and drier air into this region. So the variance is actually greater here in the Midwest, and also here in the Southwest, because we have the North American monsoon system. So it's relatively dry until the monsoon kicks in. But the thing is, if we want to combine these, that is temperature and humidity, into an index, here's the apparent temperature. This is from Stedman, did a study back, I believe it was in 1984, where he looked at the impact of not just temperature, but things like wind and solar radiation and moisture on the apparent temperature affecting the human body. If he just regressed two variables, the temperature, and E here is just a measure of the vapor pressure of the air, just a different way of looking at the humidity, he comes up with these basically regression coefficients. So he has a constant term here, and the temperature, and then this other factor times the humidity, if you will. But in this particular variable of sort of a combined index, the temperature dominates. In other words, the variability of the temperature pattern looks a lot like the variability of the apparent temperature. It's a little bit higher, as you can see, over the Midwest, because we know that we're including the effects of moisture variability, and so that increases it somewhat. But not nearly as much as if we look at the equivalent temperature, which is, again, just the ambient temperature plus the specific humidity times this latent heat of vaporization. Basically, what this is measuring physically is to say if we wrung all the moisture out of that air, what would the contribution of the latent heat be to this? And you see that it's dominated in this case by the humidity. It shows the greatest variance, and notice these are on two different scales. This one is twice as the scale as the apparent temperature. So it depends on how you define these things. All of these have been used in different ways, the apparent temperature, the equivalent temperature, and just the plain old temperature without including humidity at all, and we just want to see the variation in the behavior of these. So here's a couple of examples of heat waves using station data. This is from the Global Historical Climatology Network, and I just wanted to show this as a contrast, a couple of sort of extremes. What I'm plotting here is for each station. I'm defining a heat wave in this case as being greater than the 95th percentile for at least 3 days at an individual station. And I measure that for the minimum temperature, the maximum temperature, and then I find out if both the maximum and minimum temperature were above that threshold, both in terms of intensity and duration. So what you're seeing here is an example for May. I mean, I talked about the summer, June to August, but as indicated earlier, sometimes it's on the shoulder of the season, you know, in the spring or in the fall, where you can get heat waves. And this one's particularly interesting in that you see most of the dots here, with the exception here in sort of the central mid-Atlantic region, are green, meaning that the minimum temperature is what's defining this heat wave more than the maximum temperature, although it's somewhat greater here and closer to the coast. In contrast to an example, I think this date, by the way, is the middle of that 3-day period, defining the heat wave. We see that in this particular case, in 1980, we see a lot more gold here, meaning that it's the maximum temperature that predominates in defining this particular heat wave, although there's several stations where it's both the maximum and minimum. Predominantly, it's the maximum temperature. And so we're interested in this kind of contrast. What's leading to these two different types of heat waves? So just without worrying about these strange-looking plots, I hope you can see this. They're pretty impossible to read on the scale, but do you see this is the United States? The blue lines represent the departures from average of the upper-level height field. So essentially, you see up here in this period in 1991, we had a very large upper-level ridge, basically, in the Great Lakes region. And the little arrows indicate what the low-level winds are doing. So what we're interested in here is the low-level moisture flow that in this case comes all the way from the Caribbean up across the Gulf of Mexico into the United States. And that's what's associated with the enhanced minimum temperature more than maximum temperature. This is what we're going to call, in one sense, a moist heat wave. I could show you things like the equivalent temperature, which would verify that, or the specific humidity anomalies, and you would see that. If you contrast that with what's going on here in 1980, again, we see a ridge which is typical of these heat waves, because when we have a ridge, we tend to have clear skies. There's subsidence or sinking air in the vicinity of the high, which contributes to the heat wave. If we look at the arrows, if you can see them squinting, it's in a clockwise circulation here, indicating high pressure at the surface. And notice that if you can see them, the arrows are actually pointing in the other way from the Gulf of Mexico. In other words, the moisture is going away from the United States over the Gulf of Mexico. So that's an interesting component of this, is that when we look at heat waves in terms of diagnostics, what's ultimately, from a physical standpoint, leading to the heat wave? Excessive heat, yes. Where are we getting moisture from if it's, say, in this case here with the minimum temperature? These two plots here are just showing a simple measure of the drought condition, if you will. So this is the standardized precipitation index, 3-month value of the standardized precipitation index. So the green here in 1991 indicates that conditions were actually quite a bit wetter than average, and the white means near average. So this is a very moist period, again, as that humid air came in all the way from the Caribbean up into the eastern United States, in contrast to 1980, which of course was a severe drought across the southern plains. And this is another important contributor to heat waves from a physical point of view, because there's a strong interaction between what goes on at the Earth's surface in this region, in other words, we dry out the soil during a drought, and what goes on with the temperature. If we dry out the soil, we can increase the temperature, but predominantly the maximum temperature more so than the minimum temperature. And here's just an example contrasting two events here in the northeastern United States, just to get at what we're trying to do in this study, is to say, well, are there recurrent atmospheric patterns that lead to heat waves in various regions of the country? Augustine showed one example earlier for the central part of the U.S. We want to look at different regions. For example, here in the Northeast, here's a heat wave that occurred in 2005 during July. The red here actually indicating the anomaly of the equivalent temperature, but it's the cases where the equivalent temperature exceeded the 95th percentile for 3 or more days. And again, we're interested in where did this moisture come from. Obviously, it's not going to come from the Pacific. It's going to be coming from the Atlantic or the Gulf. but specifically how? What are the circulation patterns associated with that? And below is, again, you see the red indicating the high equivalent temperature. So without worrying about these diagrams, we're just showing here's what the upper level height patterns look like, the wave patterns associated with these two heat waves, in this case in the Northeast, and they're very different. So we're not seeing a recurrent pattern. But the bigger picture is, what can we say about that across the country for cases of looking at heat waves defined just by temperature or when you include humidity? And finally, I'll just quickly note that while this is a diagnostic study, I'm also interested in the practical side of these things, particularly from the aspect of health and energy, actually. But I'm going to show something from Kim Knowlton was on the line earlier that she can speak far more to. She's published on this. But here's a heat wave that occurred in California, I'm calling it, in 2006, because that's where the most impacts were. So this is a July heat wave. And her study was particularly interesting. If we look at what I'm plotting in the upper right, I'm sorry, I should have explained that, was this is, again, in the NAR data. We're also looking at this in the station data. But this is areas where the percentile of the daily mean temperature exceeds the 90th percentile. So if it's less than the 90th percentile, it's white, and above 90, it's going to be in some shade of the gold and red colors here. So the darkest red here over the central part of California is up near the 99th percentile over the full record of the NAR. So very extreme heat in this part of the country. But what her study is particularly interesting was when the devil is in the details when you talk about impacts in terms of human health. So if you look at, for example, at the map here, looking at the Central Valley in California was up there around the 99th percentile, but this is spread towards the coast. I should point out that this is only for one section of this heat wave, the 22nd to the 26th of July. Actually, some of these impacts were occurring, I think, back to around mid-month, maybe the 16th. But what she's showing here is the ratio of heat-related emergency department visits, basically during the heat wave to when you don't have the heat wave, so to before and after the heat wave. So in other words, the ratio here greater than 1 is telling you that there's a spike in these visits, and you can see the range here, the confidence interval here, that all of them remain well above 1. But you see along the coast here is where values are the greatest. And basically the idea here is that if you think about July average temperatures, you really have to look at a finer spatial scale than just looking at these global maps, or national maps, I should say, in that there's a lot of geographic variation, of course, in the temperature. So here's the average July temperature in the NAR. It's actually quite a bit higher in the Central Valley. Of course, it's a heck of a lot higher in the southern part here towards the desert region. But it's also cooler along the coast where people aren't acclimated to high heat. So there's different types of being acclimated to heat. There's the early season, which was Andrew talked about earlier, that they have a factor that accounts for that. But it's also geographically. If you're in a region where you typically don't see these extreme temperatures, you're also quite sensitive. So that's basically it in a nutshell. We're looking at the diagnostics of these different flavors of heat waves, if you will, seeing how the climate models reproduce what we see in observations before seeing what they say about projections. But in a broader sense, I'm particularly interested in as well, what are the impacts of heat waves on different sectors of society, in particular health and the energy sector. So I'll leave it there. Thank you.
Great. Thanks a lot, Brad. That was very interesting. I think, again, that we unfortunately have to move on because of the time. I want to make sure we don't go too far over, but thank you, Brad. Okay, final speaker is Chip Conrad, and then we'll hear from Hunter afterwards also. Chip, are you on the line?
Yes, I'm here.
Okay, great. I'm transferring control over to your computer.
Okay, do you see me?
No, not yet. If you could go into the Event Center and then click Quick Start, and then click Share Screen or Share My Desktop, and we'll be able to see it. Yeah, it looks good. Whenever you're ready, Chip.
Okay, thank you. So I want to tell you a little bit about some work that we've been doing here at the Southeast Regional Climate Center, and also with some funding from the Carolinas RESA team, what we call CESA. There's also a couple other partners that are involved with this, including the State Climate Office and also the North Carolina Department of Health. And so just real quickly, I'm going to give you a background on heat illness in North Carolina. I'll say some things about how we developed this model, basically a model that predicts how many people are going to go to the emergency room on the basis of how warm it is. And I'll go through and I'll show you an example of the first version of our model. I'll say a little bit about that. And then I'll have a slide or two showing the upcoming improved version, version 2.0. And then time permitting, I'll say a few words about potential applications to long-range forecast. So first off, in terms of a background, North Carolina is a very diverse state. You can see in the western part of the state we have the mountains where it's obviously much cooler, and the Piedmont and the coastal plain. And in terms of temperature, of course, it's generally hotter and so forth as you go into the Piedmont and the coastal plain. From work that we've done here at the center, we've identified really amazing differences in the vulnerability of people to the heat, and specifically the number of people who go to the emergency room because of heat. And so if we look across here, you see the dark blue areas. Those are basically areas of the state where the rates of emergency room visits for heat are quite low, in contrast, obviously, to the red, where they're very high. And so there's basically an 8-fold difference in these two areas here. And if you're familiar with the geography of North Carolina, one thing you might notice is that the populated areas of North Carolina, this would be Charlotte, going up to Greensboro, Winston-Salem, then over here to Chapel Hill, Durham, and Raleigh. These populated areas, by and large, the rates are quite low. And so it's very interesting that here in North Carolina, people in rural areas are much more vulnerable than people who live in urban areas. When we focus in on these rural areas, where you see these true red colors here, those are places where there's a lot of agriculture, and specifically it's labor-intensive agriculture. And even if we look inside of that, when we go down here, particularly in this sort of hotspot area here, there's a lot of produce that's grown in this area. So it's very clear that the people who are most vulnerable are those who work outdoors, and we see that a lot more in rural areas, particularly in areas where there's a lot of agriculture. Okay, so basically my former PhD student, Maggie Sugg, myself, we developed a model basically that relates temperature, daily maximum temperature, to the number of people who go to the emergency room. And so we really had this great database called the North Carolina Disease Event Tracking and Epidemiologic Tool, or NC-DETECT for short. And basically it provides a virtual census of data on emergency room visits across the state. And so basically what we did was we identified all visits that were diagnosed basically as heat illness, and this would be a primary, secondary, or even a tertiary diagnosis. And so we grabbed the age of the patient, the gender, the date of the visit. Specifically, this was ICD code 992 for heat illness. And we also got the billing address all the way down to the zip code level. And so we took every one of those visits, and then we associated those with the nearest weather station. And so you can see them here in this plot. There's a variety of networks that we used here. But we grabbed the daily max temperature, and we also, and this is sort of later work, in version 2, we identified the highest heat index each day. And so basically in the model then that we developed was one, again, where we basically wanted to predict the average daily ED visits. We standardized that by population, so basically per capita, looking at that across different temperatures. And what you can see here, this is a plot for the entire state, and as you can imagine, for days in which it's quite cool, there's very few emergency room visits. When we get up to a daily maximum around in the mid to upper 80s, the slope begins to increase, and you can see here going through the 90s, the slope goes way up. Okay, the slope is maximized here. And then very interestingly, right around 100 degrees, that's where we see the most visits. And then it plummets, as you can see here, that when the daily max temperature gets above 100, people apparently really, become aware of the fact that it is really hot, and so they're taking precautions. And so that was something that we definitely didn't expect to see. Okay, and so what we did then was, again, recognizing that the state is very diverse, we basically broke the state up into 4 regions on the basis of the degree to which an area, and we did this all the way down to the zip code level, how metropolitan it was on sort of basically on the left side, you can see there, all the way down to very rural. So basically 4 categories there. And so we looked at the emergency room visits for these 4 different areas. You can see here in this plot, see here the green, the rural isolated, so these are the most rural parts of the state, and what you see there is that you see markedly more visits in those areas as compared to what we call rural town, which is still quite rural, and then basically metropolitan rural, so rural areas close to cities. And then lastly, again, metropolitan areas where the rates are much lower. Okay, and so we also then we grabbed census data, and so we were able to get a lot of age information here. This here basically shows us going from very young over here on the far left to very old over on the far right. But basically what we see here is that the highest rates of heat illness occur for those 18 to 44. And of course, most of you are somewhat familiar with the heat, and this might surprise you. You'd say, well, I know it's the young and the old, and especially the old, that's most vulnerable. And indeed, you see the rates are relatively high for the old. But here in North Carolina, when it comes to heat illness, it really relates to exposure and exertion. And so when we look at these particular bars here, the blue and the green, you can see there rural town and rural isolated. So the most rural areas is where you really truly see the highest rates here. Okay, and it's basically the relatively young. And if we were to break this out by gender, we would see that the rates for males are much greater than the rates for females. Okay, so I'm going to tell you now a little bit about the current version of our tool. So basically, and this part of it, so a true collaboration with the North Carolina State Climate Office. So they're the ones that actually coded this up and built this web-based application. Okay, but this model here then basically inputs National Weather Service maximum temperature forecasts. These are point forecasts, and translates these values into predictions on the number of cases of heat illness. And the way this is set up, we have different models, and so basically a user can identify a county or a region, and these are kind of divided up in terms of how rural or how urban they are. And and this is kind of going to the future, but we can potentially have models that basically zoom into age groups and gender. So for example, we've learned that males 18 to 45 in rural areas are most vulnerable, and so you can look at this and basically say, okay, looking at National Weather Service forecast for the next 5 days, how many visits might we expect? Okay, and so anyway, so this is what the first version of the interface basically looks like. And so then I wanted to show you an example here of the output. Okay, and I know we're getting really short on time here, but just very quickly, the output is presented so that we basically have the model, what the model predicted over the last 10 days or 7 days, and then the dashed lines here show basically model projections going into the future. And so the model projections actually are green here, and so you can see here during this period going back several days. So this is for August 10th, so going back over the last week or so, we can see that the visits were relatively low, and then you see them begin to go up, and then they basically peak on the 10th, and then the National Weather Service forecast then is used to forecast into the future, and you see the rates beginning to go down. The red line here is basically the baseline, so this is that's the number of visits we would expect for this time of the year. And so I just kind of pulled this from a small place in rural North Carolina, Lumberton, North Carolina, which is in Robeson County. And down here, this basically shows the plot of the maximum temperatures. And so on that day that was really hot there, August 10th, it got up to 96 degrees there. And so you can see there that the rate was quite high on the order of about 1.75 expected visits there per capita, whereas on a typical day in early August, you would expect on the order of about 0.5 expected visits per capita. So much greater here. The shading here basically is the confidence bounds here of the estimate. Okay, so the upcoming second version of the model, which we hope to complete here over the next month, the major upgrade here is to utilize the 18Z heat index, which is very highly correlated with the daily maximum heat index. And this plot here basically shows the degree of fit here. So we've got expected number of ED visits, and so that's being predicted on the basis of maximum temperature. Okay, and so you can see the maximum temperature here. You can see the plot. You can see here that it's a decent model here, but you see there's quite a bit of variability. When we compare it then with using the daily or using the 18Z heat index, you can see here a somewhat better fit. Okay, and so the variations around here aren't quite as great as for maximum temperature. So it's truly a much better model, and that absolutely makes sense, right, because we know heat index incorporates the moisture. Okay, the second upgrade that we're making is basically to provide a measure of the level of danger, and so we've come up with a scale that's basically modeled after the air quality index, the AQI here, and so I just sort of basically put this up here, and so basically it's for every day that a forecast is made, there's a color given that relates to the degree of health concern. And so just to kind of give you a sense of what this looks like, so this is a plot here showing early, this is going back to last summer, basically the 6th of June, going all the way up towards the end of June here. So our predictions here is this dashed dotted line, and the colors you see here in the background, of course, relate to the degrees of danger. Obviously, the hotter color is getting up to the top. And so, for example, if we take 6/13 here, this particular day, so the projection is well up here into the red range here, you know, which we can associate with being very unhealthy. Okay, and so that provides an example. We're working with public health people. We've been working with them on this, and we're going to engage them across the state on this tool over the summer. And so we expect to make some big tweaks here. The huge question is, well, where do we set these levels here in terms of the thresholds to go from basically one color to the next? And then just, I know we're just about out of time, and I really don't have the time to go into this here, but I just had sort of some beginning thoughts here on how this might be applied to the long-range forecast. Very quickly acknowledge Maggie Sugg. She's now an assistant professor at Appalachian State, so she did a lot of the modeling. She got some grants here that supported this. You see that there. We've worked very closely with North Carolina Department of Health and also with the North Carolina CDC BRACE program and also the North Carolina State Climate Office. If you want to see what this tool looks like, here's the web address for it. So thank you very much.
Great. Thanks a lot, Chip. Do we have a quick question for Chip, either here in the room or online? It's getting a little late, so Chip, thank you very much. That was a nice cap to all the talks. And so our final speaker is Hunter Jones from CPO, and Hunter is going to talk a little bit about NIHIS. Hunter, I'm looking for you on the WebEx. There we go, I got it.
You are in the same room. You could.
No, I don't want to have to. It's actually easier to do this than transferring the file onto the computer, probably.
Yeah.
So, and then just share your screen with us, Hunter.
Okay.
So Hunter's going to talk a little bit about this new initiative in the Climate Program Office, the National Integrated Heat Health Information System, which is something that he and Julie are both heading up here.
Do I get a prompt?
No, you got to, in WebEx, go to Quick Start and then share screen or share my desktop.
Can I just thank some of the participants on the phone who are also partners in NIHIS? It's actually, this webinar is highlighting a lot of the CPO research that allows us to do the prediction and application, but it's a big partnership activity and started with CDC, and then you've heard already from Kim at NRDC. So thank you guys who are partners for joining.
Yeah, okay, so let me quickly pick up from there. So I learned a lot from the presentations today, and they're just a small sample of the fantastic work that's being done to improve understanding and prediction and societal resilience to extreme heat. We could have a webinar like this every day or every week, and we'd never be able to cover all of the great work that's being done. So in acknowledgement of this, as Julie mentioned, NOAA and CDC came together and developed the National Integrated Heat Health Information System, which was launched by a White House announcement in June of last year, so it's not even quite a year old formally. But it has the goal of facilitating an integrated approach to providing a suite of decision support services that reduce heat-related illness and that can mitigate other effects of extreme heat. And so what this looks like is there are a number of components that we're kind of paying attention to and that we'd like to have be a part of the NIHIS. Improved prediction is the one that was talked about the most today, though some other ones were talked about as well. We bring together all these different components, and we acknowledge that we need to define the, so in addition to the predictions, we need to define the demand for this information. We need to understand the decision context of users. We need to know what's needed at different time scales. So we need to understand how this information will be used, and that will inform the predictions that we develop. We also need to improve the way we communicate this information to decision makers to make sure it's the most useful that it can be. And we also need to build capacity, because the best information, the best predictions, the best understanding of demand isn't really useful if people don't have the capacity to act. So there are a lot of components that we want to really pay attention to in NIHIS. And these components are active within the NIHIS framework, which operates at lots of different scales. It's envisioned as being active at the international, national, regional, and local scale. So it's really a global network that integrates our partners' knowledge, experience, and activities to effect a coordinated response to heat health at many levels. It's designed to allow for knowledge sharing and co-development of information in support of heat health risk reduction across all the levels that you can see here. And for example, approaches to reducing heat risk that have been very effective in the southwestern United States at perhaps a local or regional level might be really useful in parts of India, or vice versa. And so NIHIS is created to make these connections at all these different levels of the framework. And it wouldn't be possible without partners at all these different levels. So this is just kind of a sample of the partners we have at all these levels. There are many other people that are already involved with NIHIS in the short year or so that we've been at this. At the international level, WMO, WHO, with coordination and facilitation. The Natural Resources Defense Council is a great example that's active at this level. They're critical to NIHIS because they're working with local and national organizations in India, such as the India Meteorological Department and the Public Health Foundation of India, to develop heat action plans. And so that's information that's really beneficial to other partners in the network. Now we're also active at all the other levels. I don't want to belabor the point too much because I know everyone's probably ready to go home. So I'll just get to the next slide, which shows you kind of geographically where all of these partners or these active locations are. So we have a number of pilots at the local level that we're very heavily invested in right now in the United States, and then also a number of international, I wouldn't call them partners, but they're just international engagements with these different locations where we have the NIHIS network active. And if you're looking at this and you're wondering what are you doing in my location or what are you doing in my region, you don't see something, we would love to talk to you and to see how we can engage with you and understand what you're doing regarding heat health in your location. Particularly the domestic pilots that you see there in the Northeast and the Southeast and the Southwest, those are intended to answer, they're all supposed to answer questions that are unanswered, but those in particular are intended to answer some really critical questions that we've discovered in talking to our partners that are engaged in this network. How do you build institutional capacity? How do you bridge all these different institutional partners that may not always be talking together? So how do you bring the public health people together with the meteorological people to set the right threshold for emergency alerts for heat, for example? Also, on that note, what are the best parameters to be predicting? I know that many different parameters were talked about today. Some were temperature and some were a heat index. So what's the most effective? That's still an open question as it relates to certain vulnerable populations. It might not be the same answer everywhere. What data and forecast products are needed and what engagement and communication strategies are effective for different populations. Again, they might not be effective in the same way for all the different types of populations that we're engaging. So a lot of open questions that we'd like to answer. That was a really quick overview of the kinds of things we're doing with NIHIS. So you might be wondering what we're up to next. And we have two really important events that are coming up soon. One is the actual launch of the web presence of NIHIS, which will begin to make available some of the case studies, tools, reports that our partners have generated so that people can start to read them and we can integrate all those resources in one place. So look for that to happen on the 23rd of May. The URL is not there yet, but if you look at the bottom of the slide, that link will take you to a place where you can sign up for a mailing list for more information on NIHIS. So if you sign up for that, you'll definitely be able to get an announcement when that's available. And lastly, coming up on the 26th of May is a webinar that's being hosted by OSTP and the National Security Council, and on behalf of a number of agencies, many of which are listed actually on the left, NOAA, CDC, FEMA, DOD, et cetera. They're all coming together to put on a webinar that talks about what different vulnerable populations exist and how to serve those different populations in extreme heat events, not only during the event, but how to plan for servicing those populations. So outdoor workers being an example of a vulnerable population. Julie, did you have anything you wanted to add?
Just two things. One other, the web launch and the White House webinar are actually part of an effort from OSTP and the National Security Council to get ahead of the heat season. And the other piece that we probably should add up there, it just occurred to me as you were talking about it, is that FEMA for the first year has actually added heat to its list of extreme events. So it didn't do heat before, and now there's a National Heat Week as a part of FEMA's Prepare-a-thon, and it's May 22nd through 28th. So we're launching NIHIS as the backbone of that. That's why all the agencies are coming together. It will give us a great deal of visibility, and there'll be some Weather Channel specials and all kinds of stuff about heat for that week. So if you're doing anything on heat that you want to make sure that we know about, if we can highlight it, let us know, because that's going to be the week. And then the only other thing I wanted to mention was that there's back to Hunter's questions that we're asking across the pilots for the U.S. So we're actually working with the international partners. Right, like this week, there is a climate outlook forum in Sri Lanka addressing heat, and the partners that are already working on heat are beginning to ask those questions of their projects so that when we come back together in a year, we can do some co-learning about all these things so that we can begin to figure out what are the most optimal national products to produce and what are the right parameters. So everybody's working really hard on their pieces, and this is an attempt to coordinate the learning when we come back together. So otherwise, that was it. Thank you. Great job.
Yeah, thanks, guys. That was a nice overview. So that's a wrap on this webinar, and I want to thank everyone for speaking. I think, hopefully we were able to demonstrate the type of end-to-end research that CPO supports, and also how things like NIHIS can kind of wrap that all up into, a package to deliver things to the community. Let's see, I want to thank the speakers for taking the time. Andrew, thanks for joining so early in the morning from Australia. And we did record this webinar, so we'll post it on our website along with the PowerPoint slides if you would like to share that with anyone. And you can also sign up for our webinar email list if you're not already on it. And that's about it. Keep appraised of our website for future MAC webinars. We'll probably have 2 or 3 more this year, TBD on the topics. And thanks, everybody. Thanks for hanging on late on the East Coast.
Thanks for organizing it.
Thank you very much.